In the last module, we gave an introduction to LTL. We saw some examples and we gave an intuition as to which words are satisfying which LTL formulas. In this module, we will be more precise. We will give precise definitions for when a word satisfies an LTL formula. This is going to be the semantics of LTL. By semantics, we mean the meaning of LTL formulas. Let's start easy. Let's start with the set of infinite words over power set AP. This is assuming that I have AP, which is a set of atomic propositions. Power set of AP is the set of sets of atomic propositions. And we look at words formed using letters from this alphabet. We have seen this multiple times. When we say P1 is always true, this will give us the set of all words over AP_inf such that each letter contains P1. Right? How do you write it? The set of A0, A1, A2, etc. This is a sequence. This is a word in AP_inf such that each AI, which is a letter from the alphabet, power set AP, contains P1. Look at this word. Here A0 is the set P1, A1 is P1 again, A2 is P1 again. Each AI contains P1. So this word satisfies the property. Similarly, this word satisfies the property. Given a property, it is just a set of words that satisfy the property. P1 is true at least once and P2 is always true. This means that the set of all words where there exists an I such that P1 is true. For example, here there exists an I where P1 is true and P2 is always true means every AJ contains P2. Look at this. Every AJ contains P2. Here also every AJ contains P2 and there exists an I containing P1. This is to let you know that a property can be written in this form. The set of words such that something is true or false in the AIs. A property over AP is a subset of AP_inf. AP_inf is the set of all possible words and a property filters out some words from this set. So a property is a subset of AP_inf. We claimed in the previous module that LTL can be used to specify properties, which means LTL can be used to describe subsets of AP_inf. Essentially, given an LTL formula phi, we can associate with it a set of words. Every phi can be associated to words of phi. This words of phi is going to be the set of words that satisfy phi. Of course, this set of words is a subset of AP_inf. And they are essentially the set of words that satisfy phi. Okay? This is how we are starting this module. We say that with every LTL formula phi, you can associate a subset of AP_inf. A subset of AP_inf is just a set of words. So essentially with every LTL formula phi, you can associate a set of words. In this module, we will be seeing what is the set of words that is associated with each LTL formula. Before doing that, we need to say When does an infinite word satisfy LTL formula phi? Essentially, this set is a set of infinite words, right? So this should be infinite words. To get the set of words that satisfy phi, we need to define when a word satisfies phi. So that is the question asked here. When does a word satisfy the LTL formula phi? Let's take some word sigma given as A0, A1, A2 and so on. So this is a word. Each AI is a set of atomic propositions. Now, let us try to reason about smaller LTL formulas first and then talk about more complicated ones. We know that every LTL formula can be broken down using these rules. Let's start with true. When does a word satisfy true? Every word satisfies true. There is no constraint. In particular, every sigma satisfies the LTL formula true. Okay. What about pi? Sigma satisfies pi if the first letter contains pi. We saw this in the last module. Here is the precise definition. Sigma satisfies pi if the atomic proposition pi is present in A0. Okay. Now what about this? When does sigma satisfy phi1 and phi2? Easy. Sigma satisfies phi1 and phi2 if sigma satisfies phi1 and sigma satisfies phi2. You may wonder what additional knowledge does this statement give. We will see later during the definition of words that this indeed makes a difference. So this is a formula phi1 and phi2, but this is just a notation, right? And this says that a word satisfies this formula if it satisfies both phi1 and phi2. What about not phi1? Simple. Sigma satisfies not of phi if sigma does not satisfy phi. Okay. What about x phi? These are more interesting. Sigma satisfies x phi. Sigma is A0, A1, A2 if the word obtained by cutting A0. Look at A1, A2, etc. This word should satisfy phi. Okay. For example, if I said x of phi, A0, A1, A2 satisfies x of phi if A1, A2 so on satisfies x phi, which means A2, the word starting at A2 satisfies phi. Okay, that is how you give the meaning for more complicated formulas, but for now you learn that sigma satisfies x phi if the word obtained by cutting A0, or in other words the word starting from the position A1 satisfies phi. Now comes the last and most important operator, until. When do we say that sigma satisfies phi1 until phi2? There should be some point j such that the word aj plus 1, when you cut sigma, you find j and you look at the rest of the word aj plus 1 and so on, that word should satisfy phi2, and until that point, so a0, a1, a2 till aj minus 1, you look at every point here and you look at every word starting from these positions These words should satisfy phi 1. In the last module, we had simple formulae like P1 until P2, where we said that there is a J where P2 is true until that point P1 is true. But in general, these phi 1 and phi 2 could be LTL formulas themselves. They could have an until here, phi 2 could have X and untils and so on. So we need to give this generic definition where we have to say that every word starting from I satisfies phi 1. For example, if it was just P1 until P2, there exists a J such that Aj plus 1 satisfies P2. Now, when does a word satisfy P2? When the first letter of that word contains P2. So here Aj should contain P2, and all words from AI, 0 to J minus 1 should satisfy phi 1. Here it is P1, which means P1 should be in AI for all I between 0 and J. So in the case of P1 until P2 it was easy, but when we have generic LTL formulas, you need to have this definition. As an exercise, please look at the examples of LTL formulas that we saw in the last module and try to write when sigma satisfies those LTL formulas. We had given you an intuitive meaning of when does a word satisfy it. Try to match your intuition with the definition. Try to see, for example, if it was not of x phi 1 or rather not of x p1 until not p2. If it was a formula like this, you know intuitively that not of x p1 should be true until not p2 is true. Try to write the definition. Replace phi 1 with whatever is there here. Replace phi 2 with whatever is there here. Then recursively write what this means using the definitions here, and you will understand that whatever you had in your intuition actually translates, and then you will be able to understand the definition better. We have explained in the previous slide when a word sigma in APinf satisfies phi. We have said when sigma satisfies phi. What is the meaning of sigma satisfies phi? So you break down phi according to this grammar and try to keep writing the definition recursively. So the set of words phi, this notation stands for the set of all words that satisfy phi. Let us now try to characterize this set words of phi. What about words of true? Since every word satisfies true, words of true will be the entire set APinf. What about PI? PI is an LTL formula. The set of words of PI is going to be the set of all words such that PI is in A0, A0. Okay? So with the LTL formula P1, you associate a set of words. And what is the set of words? It is the set of all infinite words that have P1 in the initial letter. That is it. Hope you understand this definition is the same as the easy sentence, the set of all words where P1 occurs in the initial letter. What about this? What about words of phi 1 until phi 2? They are the set of all words which satisfy phi 1. That means they are in words of phi 1 and they are also in words of phi 2. Which means words of phi 1 and phi 2 is just the intersection of words of phi 1 and words of phi 2. Now you see, writing it down like this gives us a way of expressing the sets. Now what about sigma satisfies not phi? Words of not phi is going to be the set of all words in the complement of words of phi. You look at the set words of phi and just take the complement set. This will give you the set of all words that do not satisfy phi. What about x phi? Words of x phi is the set of all words such that a1, a2, etc. This word a1, the suffix starting from a1 is in words of phi. Similarly, we can write what is the words of phi 1 until phi 2. It's the set of all words such that there exists a j where aj plus 1, the suffix starting from aj belongs to words of phi 2, and all suffixes starting from i's between 0 and j minus 1 will be in words of phi 1. That means a naught, the word a naught, a1, a2 is in words of phi 1, a1, a2 is in words of phi 1 till j minus 1. Okay, you might ask this question, suppose j was 0 itself. Suppose the word a naught, a1, a2 already satisfies words of phi 2, then you don't have this statement at all. You will just say that a naught, a1, a2 satisfies words of phi 2. You don't need phi 1 to be true anywhere because phi 2 is already true in the first step. It is important to understand the intuitive meaning of these formulas. This technical jargon is just for completeness sake. I would also like to point out that although this looks full of notations, if you try to understand it step by step, it is going to be easy. Let us now try to write the semantics for f phi. F phi, as we saw, is just true until phi. Sigma satisfies true until phi. When I will replace phi 1 with true and phi 2 with phi, you will get there exists a j such that aj plus 1, this word satisfies phi, and for all 0 less than or equal to I less than j, as in for all I between 0 and j minus 1, ai plus 1, this word satisfies true. Of course, this statement would be true for any word a naught to a, whatever the a naught to aj minus 1 is, no matter what a0 to aj minus 1 is, this is going to be true because the word, the LTL formula true contains all words, right? Every word satisfies true, so words of true is ap inf. So no matter what a0 to aj minus 1 is, this statement is true. So we will just remove it. And what we have is that sigma satisfies true until phi if there exists a j such that the word aj plus 1 satisfies phi. This was the semantics of f. If phi had been p1, say, this would have boiled down to saying there exists a j such that aj satisfies p1. What about g of phi? G of phi is not of f of not phi. You know this. It's not the case that at some time you reach a point where not phi is true. Let's try to write the semantics. First, let us write when a word satisfies f of not phi. We just copy it. Instead of phi, we put not phi. Sigma satisfies f of not phi if there exists a j such that the word aj plus 1 satisfies not phi. Now, when does sigma satisfy not of f of this if sigma does not satisfy f of not of this, right? So this is this formula, not of f of not phi. Sigma satisfies not of f of not phi if sigma does not satisfy the thing inside the negation. So what does that mean? you need to negate this statement which says that there exists a j such that aj plus 1 satisfies not phi. And what is the negation? All j satisfy phi. Okay, let me go through it once again. Sigma satisfies f of naught phi if there exists a j such that aj plus 1, this word satisfies naught phi. So I'm just replacing phi with naught phi here. So don't worry about it. Now comes this negation. When does sigma satisfy not of this? Clearly sigma satisfies not of this if it does not satisfy the formula inside the negation. So when does it not satisfy the formula inside? When this is not true. That means there does not exist a j such that aj plus 1 satisfies not phi, which means all j satisfy phi. Okay. As I said before, this is just for completeness sake that I am giving these precise formal definitions. As long as you understand the meaning of G and F through examples, it's well and good for using model checking tools. So let's give an example of a transition system and a formula phi. When does a transition system satisfy the property given by LTL formula phi? We know that a transition system satisfies a property P if the traces of the transition system are contained in the property. If the property is given by the LTL formula, this just means that traces of the transition system are contained inside words of phi. Now you can go through the mutual exclusion example that we saw before. Essentially what we were checking is the traces of the transition system are contained inside the words of the LTL formula that we give. Essentially, when we were doing our model checking with new SMV, we gave a transition system, and then if you remember, we gave check LTL spec and we gave an LTL formula. What new SMV was doing inside was to check if the traces of the transition system are contained inside the words of the formula given by given in this LTL spec. Okay. I would like to finish this module with an observation on negation. Suppose this is AP_inf. This rectangle, black rectangle gives AP_inf. For an LTL formula phi, suppose this green circle, the words inside this green circle, suppose they denote words of phi. Now everything outside this green circle is going to be the complement of words of phi. Now suppose the traces of a transition system are here. This is the set of traces of a transition system. Note that this transition system, the set of traces, are not entirely contained inside words of phi. See, it satisfies phi only if it is contained in words of phi. So, this transition system would not satisfy phi. At the same time, these traces are not contained inside words of phi complement. So, this transition system would not satisfy not of phi as well. Okay, so this is possible. A transition system need not have to satisfy one of either phi or not phi. Let's see an example. Look at this transition system. There is an execution which reaches P1 and keeps looping here. However, there is an execution where it reaches a state where P1 is not true and it loops here. So, This transition system does not satisfy f of p1 because there exists a trace which does not satisfy f of p1. Similarly, this transition system does not satisfy not of f of p1 because there exists a trace which satisfies p1. Right? In the sense, there exists a trace, this one, which does not satisfy this formula, and there exists a trace here which does not satisfy this formula, which was the negation of this. Try to understand this concept. It's an important thing that given a transition system, it is not necessary that it will either satisfy formula phi or not of phi. It's possible that it does not satisfy both of them. As we saw, this is the example. This is because we are asking, of course, given an execution, given a word, it either belongs to words of phi or in the complement. Of course, in a word, that is the case. However, when you talk about a set of words, it could intersect with both of them, so it might not be contained entirely in one of them. This is the point. In this entire module, we were talking about attaching a meaning to LTL formulas. In particular, we were trying to attach a set of infinite words with every LTL formula. Let me reiterate, for using LTL, it is enough if you understand the way LTL formulas are formed, as in the way we saw in module 1. As soon as you understand this, you can already use new SMV for model checking problems. However, if you are interested in understanding the algorithms that are going inside, you need to understand this concept of the words attached with every LTL formula.